In this section, and in this video, we'll talk about change of variables more generally. So we've already discussed changing variables. Whenever we go from rectangular coordinates to polar coordinates in 2 dimensions, or in 3 dimensions, we go from rectangular to, say, cylindrical, r, theta, and z. Right? Or we can go to spherical, which is rho, phi, and theta. So rectangular, cylindrical, and spherical, right? And in 2 dimensions, cylindrical is really just polar coordinates. Right? So we've done all this, right? They're on your formula sheets. So, you know, you're pretty comfortable with this by now, I hope. But we're going to do this more generally, right? So suppose we have just a set of coordinates, which could be rectangular, but they could also be, you know, polar or cylindrical or spherical or some other coordinate system, more generally. And we might want to switch to just some generic coordinates, let's say u and v. Right, and we're going to stick with the two-dimensional case of change of variables, right? So the u and v are just some generic new coordinates, right? Coordinates. Right. And presumably, right, x is just some function of u and possibly v as well. Right? And y is also some function of u and v. Okay, so this is sort of the more general setting. You know, just to bring it back to polar coordinates, right? X is certainly a function of r and theta, and it's a familiar relation, right? It's just r times cosine theta. And y is also a function of r and theta. It's just r times sine theta, right? Right. So yeah, the relationship between x and u and v and y and u and v could be that simple, or it could be more complicated, right? But that's the idea. And before we do this, we might want to just relate this to the single variable case. What you did in Calc 1, I presume, you have, let's say, a definite integral from a to b of some function f of x dx. Right? So you evaluate this definite integral and you just get some number. But now suppose x is just some function of, let's say, u. So, right, so we can apply a change of coordinates here, and to get your dx is just going to be, well, g prime of u, right, times du. So the definite integral now becomes the integral of f of g of u times g prime of u, right, times du. But now what are the limits, right? The limits are no longer a and b, because if you remember, a and b are values of x, right? So this is x equals a, x equals b, but now we need the corresponding values for u. And, well, it's just using this, you have to go backwards, right? You have to solve for u. So u will be, in terms of x, g inverse of x, right? So, yeah, so the limits here are g inverse of a, the lower limit, and the upper limit is g inverse of b. Okay, so that's, again, this, you know, this should be somewhat familiar. You did this all the time in Calc 1, right? It's basically just, you know, what we call u substitution. Right. Okay, so yeah, you know, in the single variable case, that's what it is. But in 2 or 3 variables, it's just a change of variables, right? It's a more general change of variables. So let's see how that works now. Okay, So instead of a single integral, it's now going to be a double integral over, again, some region R of the xy plane of some function f of x and y, dA, right? Where dA could be, dx dy or dy dx, depending on if it's a vertically simple or horizontally simple region, right? So yeah, so now we want to convert this, of course, to u and v, right? And so we can do that. Just replace x with, right, the function of u and v, replace y with its function of u and v. And now the question is, well, what's our dA, right? What's our new dA? So in the single variable case, it was just the derivative, right? Because it's just a function of, right, x is a function of u, so it's the derivative of g. So now what's the derivative here? Well, there's a lot of derivatives, right? There's the derivative of x with respect to u and with respect to v and y, right? So it's a more complicated object, right? But it is essentially just a derivative, right? It's going to be the absolute value of the following. It's going to be the partial of x with respect to u times the partial of v with respect to, the partial of y with respect to v, right? And then minus the partial of x with respect to v times the partial of y with respect to u. Again, in absolute value. So because you're subtracting, this could end up being negative, but we just want to make it positive. So just take the absolute value, right? And when you do that, you get your new dA, right? Essentially, this just becomes, du dv. Whereas before, we had, dx dy. Or let's say dy dx. Doesn't matter, right? Oops, I used a slightly different color, but that's fine. Oh, I can fix that. Yeah, so dy dx, right? So this is your dA, right? Your dy dx, dx dy in terms of u and v now, right? All right, so this complicated, set of partial derivatives here, if you just, right, so this looks weird, but you can remember this in terms of a matrix. So if you take the partial of x with respect to u, and then the partial of x with respect to v for the first row, and then the second row is the partial of y with respect to u, and the partial of y with respect to v, right? If you take the determinant of this, right, the diagonal, multiply the derivative of x with respect to u times the derivative of y with respect to v, minus, right, the derivative of x with respect to v times the derivative of y with respect to u, right? So the determinant of this, I'll just abbreviate determinant det, right? This is called the, if I can spell it right, the Jacobian, right? For the change of coordinates, right? For going from x to u and v, well, in general, from x and y to u and v, right? Okay, so yeah, when you're changing coordinates from x to x and y, right, usual rectangular coordinates is usually how we set it up, right? Then you have to multiply by the absolute value of the Jacobian determinant, right? So you have to take the determinant of that. Yeah, the Jacobian is just a matrix. So maybe let me erase determinant. Yeah, so it's not the Jacobian is not the determinant, right? The Jacobian is just the matrix. So what you're multiplying by here then is the determinant of the Jacobian. Just to make that clear. Okay. So let's just do one quick example of this. And it's the old familiar one, right? Let's suppose that x is polar coordinates, right? R times cosine theta. and y is r times sine theta. Okay, so we have 4 partial derivatives to take, right? Start with the partial of x with respect to r. That's just cosine theta, right? You've done this before, right? You did this in the homework on the last test, I think, probably. And the partial of x with respect to theta is going to be negative r sine theta, right? And then the partial of y with respect to r is going to be sine of theta. And the partial of y with respect to theta is going to be r times cosine theta, right? So let's just take the determinant of this, right? Consider this to be the, so the Jacobian, I guess I'll call it J, for lack of a better letter for Jacobian, is just the following matrix, right? It's cosine theta minus r sine theta in the top row, and the bottom row is sine theta and r cosine theta. So now take the determinant of J, and you get r times cosine squared theta minus, minus a negative r times sine squared theta. But minus a negative is positive. I can factor out the r. So cosine squared theta plus sine squared theta, you immediately recognize that is just 1 times r. So the determinant of the Jacobian is r. No surprise, right? We talked about this some sections ago when we were doing double integrals, right? In rectangular, we convert from rectangular to polar coordinates, and we had that mysterious r in there, right? R times dr d theta. And before I explained, we need the r because otherwise it wouldn't have units of area, right? It would be a length instead of an area, right? Meters instead of square meters. But again, that didn't fully explain why it's not, 3 times r or pi times r or some other multiple of r. That it's just r itself. And now we know why, right? It's just the Jacobian, right? So we get the r from the Jacobian matrix, the determinant of the Jacobian. Okay, so that hopefully explains where this r comes from now. It just comes from the Jacobian for converting from, well, in this case, from rectangular to polar coordinates, r and theta, right? And the same goes for 3-dimensional coordinates, right? So if we want to go from, say, rectangular, z, to cylindrical, right? Now you're going to have a 3-dimensional determinant, right? You're going to have partial of x with respect to r, partial of x with respect to theta, partial of x with respect to z, and so on, right? I guess I'll write it all down just once here. Oh, yeah, that's right. I forgot z is in both. Partial of z with respect to r, partial of z with respect to theta, and here's a fun one, partial of z with respect to z, which of course is just 1. So, yep. So when you work out all these partial derivatives, again, it's not hard to work out, right? Partial of x with respect to r is just cosine theta. Partial of x with respect to theta is minus r sine theta. So this is really just the same as it was for polar coordinates here. And then partial of x with respect to z, well, x doesn't depend on z, so that's 0. Y doesn't depend on z, so that's 0, right? And z doesn't depend on r or theta. And the partial of z with respect to z is 1. So when you take the determinant of this, of course, you still just get r. And so, yep, the Jacobian for cylindrical coordinates is r dz dr d theta. Again, we already knew that, but now that explains maybe why you get that extra r. Okay, and finally, if you want to go from, say, rectangular to spherical, I guess we'll do the phi first, and then the theta. I think that's the usual order. And just to remind you of the conversions, again, these you should know by now. Phi. Y is rho sine theta sine phi, and z is rho cosine of phi. So now you have the corresponding determinant with respect to x with respect to rho, x with respect to phi, and x with respect to theta. And then the same rho, but the y partials, right? Or the partial of y with respect to the same three variables. Phi, and then theta, right? So, yep, so the matrix will be a little bit more complicated here. With respect to rho, you're just going to get cosine of theta sine of phi. And I'm going to go down instead, because the rho partial of y is just sine theta sine phi. And then the z partial of rho is just cosine of phi. Right. Now, with respect to phi, the derivative of x with respect to phi, right? It's going to be rho cosine theta cosine phi. And then for y, rho sine theta sine phi. Oh, sorry, the derivative of sine is cosine. I forgot to take the derivative, right? So sine theta cosine of phi. And then z with respect to phi is going to be negative rho sine of phi. Right. And finally, with respect to theta, the last column here will be, let's see, minus rho sine theta sine phi, rho cosine theta sine phi, and z with respect to theta, is 0. Z does not depend on theta at all. Okay, so that makes it a little bit easier. Now to calculate the determinant. So that is going to be a lengthy calculation, and I think this is one that you might want to work out yourself, right? So you know how to do determinants. I would actually expand on this row here, the bottom row, because you have that 0 in there. So that should make it a little bit easier. So essentially you multiply cosine times this determinant, right? And then minus this, so that should end up being a positive this, times this determinant by getting rid of the middle column here, right? So yeah, it's a bit of algebra, right? It's not simple. It takes, maybe 3 to 5 minutes to work it all out. So the determinant of this Jacobian here, well, hopefully won't be a surprise because we've seen it already. It's rho squared times sine phi, right? So you work all this out and you get rho squared times sine phi. And that should explain now why when we switch from rectangular to spherical, right? Oh, I keep putting the theta first, although it really doesn't matter. That your dv is now rho squared sine phi, d rho, d phi, d theta. Okay. So, yep, you're doing a triple integral, and this is your new dv. So don't forget the rho squared sine phi. Otherwise, it's just not going to work out correctly. All right, so that's the Jacobian, right? That essentially allows us to change variables from x and y, or x, y, and z, to essentially any variables we want. Now, the only ones we know of right now are cylindrical and spherical, and polar in 2 dimensions. But of course, there are many other coordinate systems. Some maybe not so useful, and then others might be more useful. So let's see, in sort of the more general context of a different set of coordinates that we might want to use. Obviously, if you have radially, symmetry that's with respect to the z-axis, you might want to use either polar or cylindrical. If you have symmetry with respect to the origin, then you might want to use spherical coordinates. But again, those are not the only change of coordinates, so let's see what others might look like. Okay, So here's one I stole from the homework again. We want to just find the Jacobian for the change of variables x is equal to uv minus 2u, and y is equal to u times v, right? So again, why this change of coordinates? Again, we don't know why this is going to be relevant or important, but let's suppose we do want to change coordinates from x and y to u and v. So what would be the Jacobian here, right? So the Jacobian is, again, just the matrix partial x with respect to u, partial x with respect to v, right? And then the second row will be partial of y with respect to u, partial of y with respect to v. And I think in this case it's pretty easy to do. The partial of x with respect to u is just v minus 2. Partial of x with respect to v is just u, right? Partial of y with respect to u is v, and partial of y with respect to v is u. Did I get that right? Partial of y with respect to v. Yeah, I think so. Partial of x with respect to v, yeah, is u. Okay, so I think that's right, right? So that's the Jacobian. But now, if you want to do a double integral, you want to take the determinant of the Jacobian, which is this diagonal, right? So u times v minus 2, and then minus this diagonal, which is u times v. So uv minus 2u minus uv, and uv minus uv, of course, is 0. So we just get negative 2v. Sorry, negative 2u. Right. So that's the Jacobian, right? So now, if I want to do a change of variables from x and y, let's say dy dx, and I want to change to a double integral as a function of u and v now, over the same region, although, again, you have to express the region instead of x and y coordinates, it's expressed in u and v coordinates. So we'll talk about that in just a minute. But yeah, so it's not just du dv here, right? It's going to be, well, don't forget there's also the absolute value, right? So yeah, so this symbol means determinant, and this symbol means absolute value. Then you do du dv, right? And so it's going to be a positive 2u because of the absolute value, right? These are integrals here. F of u and v, and yep, so 2 times u times du times dv, right? So that's the dA in the coordinates u and v, right? Yeah, so that's how it works, right? You can, we'll do one more example of finding the Jacobian, and then we'll figure out why we might need to convert these coordinates to these, what looks to be some random set of variables here, right? U and v and x and y. But again, in some problems, it'll make sense. Maybe not as much sense as, r theta and, rho phi and theta. But in certain instances, these u and v's might work out great, right? Okay. Okay, so here's another change of coordinates, right? X is 1/3 of the quantity 4u minus v, and y is 1/3 of u minus v. First thing you might want to do, of course, is multiply by the 1/3. So this is 4/3 times u minus 1/3 times v. And this is 1/3 times u minus 1/3 times v, just to make that a little bit easier, right? And so these are just linear functions, right? There's no u times v, there's no u squared or v cubed or square root of u, right? So this should work out pretty well. The Jacobian, just to remind you, partial of x with respect to u, partial of x with respect to v for the first row, partial of y with respect to u, partial of y with respect to v. And let's just do that in our heads here. This is going to be, we're going to do the determinant in just a minute. Right, so partial of x with respect to u is just the 4/3. With respect to v, it's negative 1/3. And then the partial of y with respect to u is positive 1/3. Partial of y with respect to v is negative 1/3. And when you take the determinant, you get 4/3 times negative 1/3 minus negative 1/3 times 1/3. So this is going to be negative 4 over 9 plus 1 over 9, which is negative 3 over 9, or negative 1/3. So that's the determinant. However, if you want to go from a double integral of some function of x and y, right, and you want to use u and v instead of x and y, then you take the absolute value of the determinant 1/3, right, and you just get positive 1/3. Right, and then this will be, you know, du dv, right? So this is our dA here, right? Okay, so yeah, in this case, the Jacobian is just a constant. That can happen. You saw in the previous example that I erased already. It could be a function of u, or a function of v, or a function of both u and v, right? The Jacobian for polar coordinates just involves r, right? It doesn't involve theta, right? And the same thing for cylindrical. Just involves r, not theta or z. But in spherical, right, it involves both rho as rho squared, and it involves phi. And the only one it doesn't involve is theta here, right? So yeah, in general, your Jacobian could be a function of u or v or both, right? Or in 3 dimensions, it could be a function of all 3 variables in some cases. But in some cases, in very simple cases where you have these linear relations, it could be just a constant, right? Okay. So with that, now we can ask the question, well, why is this even useful, right? Why would you ever need to do something like this? And it just depends on what your region R looks like, right? So as an example, let's suppose that our region R here is this awkward region, this little parallelogram, right? And, you can check that it is a parallelogram, right? We have the 4 corners, the 4 vertices. Right, so this is our region R here. It's basically the parallelogram determined by these 4 corners, right? And we have this set of coordinate changes from x and y to u and v, and it's the same one in the previous example, right? So now we're going to see why this might be a useful thing to do here, right? So it just has to do with changing from x and y to, say, u and v. And I'm going to draw this in a particular way here, as you'll see why in a second, right? So all these points here are x's and y's, right? So the 6, 3 is the top corner here of the region R of the parallelogram, with an x coordinate of 6 and a y coordinate of 3, right? So our goal is to get these points into the u and v plane, right? We want to transform them so that we get u and v instead of x and y. Okay, so what's that going to involve? Well, let's suppose, first of all, if x and y are 0, then it's pretty clear that when you solve this system, you're going to get u and v to be 0. So that point 0, 0 doesn't change at all. That's still going to be 0, 0 in the uv plane, right? Right. But now the question is, what happens if you want to use the point, say, 4, 1? So if x is 4 and y is 1, I got to erase that, what's u and v? So yeah, you get a system of these 2 linear equations in 2 variables, and you have to solve that system, right? And you can see we're going to be doing this, over and over again. So why not just do this more generally, solve for u and v in terms of x and y? Okay, so it's essentially an old algebra problem that you did a long time ago, pre-calculus, even before that maybe, right? So yeah, let's do, first we can, I suppose we can just multiply everything by 3 here. If we multiply the first equation by 3, we get 4u minus v equals 3x. And the bottom equation, if we multiply that by 3, we get u minus v is equal to 3y, right? And, well, we can eliminate the v if we multiply the bottom equation by -1 and just add them together. That eliminates the v. We get 4u minus u is 3u, and that's going to equal 3x minus 3y, right? And now we can just divide by 3, so u is just x minus y. Right? So this is the inverse relation, right? And now, if we want to find v, we can eliminate u in a similar way here. Let's multiply the bottom equation by -4, or no, +4, I think. We want to cancel the, yeah, we want to, right. This equation here, we multiplied by -1, right? Just multiply by, I think, -4. Yeah. So this is going to be, I take that back, +4, because we want the u to still be negative, right? Okay. So yeah, we're going to get +4v, and then we're going to get -12y on the right. And that's still not right. I'm sorry, I'm just confusing myself here. This should be an x. It's not 3y. For the first equation, it's just 3x. Okay, so I just copied down the first equation. I multiplied this bottom equation by +4, and now when we add them together, we eliminate u, and we get 3v is equal to 3x minus 12y. Divide by 3, v is x minus 4y. Oops, yeah, x minus 4y. Okay, so again, we didn't have to do this. We could have just done this point by point, but now you can see the ease of transforming the coordinates here. And maybe I'll move this down a little bit here. If u is just x minus y, and v is just x minus 4y, right, now we can see that if x and y are both 0, right, we get 0 minus 0, and 0 minus 4 times 0. So we still get 0, 0, right, in terms of u and v. Right. But now, let's suppose x is, yeah, I have to write this down, xy is 4 and 1. What's u and v going to be? Right. So again, that's not hard. U is going to be 4 minus 1. And v is going to be 4 minus 4 times 1, which is 0. So we get 3, 0. Right? And then what other point do we have? We have 2, 2. X is 2, y is 2. Right? So then u and v is going to be, so 2 minus 2, right, which is 0. And v is going to be 2 minus 4 times 2, which is 2 minus 8, so negative 6. That looks like a b, right? Negative 6. And finally, all right, so yeah, 0, negative 6. And finally, I'll squeeze that in over here. X and y is the point 6,3. Oh, you know what? Just to be consistent, let's do it down here. I have a little more space, right? Okay, so x and y is 6 and 3. That was the top right corner, right? So what's u and v here? Right. So u is going to be 6 minus 3, which is 3. And v is going to be 6 minus 4 times 3. 6 minus 12 is negative 6. So we get 3, negative 6. Okay. So the four corners of the parallelogram in the xy plane now become what, right? So if we graph these 4 points here, so 1, 2, 3, 4, 2, 3, 4, 5, 6, and this is not to scale. Maybe I'll make it to scale here. 1, 2, 3, 4, 5, 6. I think I have just enough space here, right? So 0, 0 was the same. We already noted that. Then we have 3, 0. And then we have 0, negative 6. And then the last point was 3, -6, which is down here. So what do we get? No longer a parallelogram, but a rectangle. Right? So this is my new R. In fact, I should call it S, because it's not the same region. Right? That's what I was trying to warn you about earlier, that when I write R here and R here, they're really two different regions. So I should not use the same R here. I should use maybe S, because it is a different region. Although it represents the same domain, just in U and V coordinates, right? So the region R in X and Y coordinates is comparable or similar to the region S in U and V coordinates, right? All we did was transform all these points in here. So I have some generic point here, X and Y. When I do the transformation, I get some point in here, U and V, right? But we don't have to do this with all the points inside the parallelogram. We did it with the corners, and I think the corners were good enough. So just to show you, the corners here do in fact form a rectangle. Even though V is negative, you know, that might not be completely ideal, but it's the best we can do here, right? Right. So the point is, when you're doing a double integral now, it's probably easier to do a double integral over a rectangular region. We've done many of those already, as opposed to this weird parallelogram region, which I guarantee is not going to be an easy calculation, right? Because, you know, it's not exactly vertically simple or horizontally simple. You have to divide it up into maybe three regions or so. So not a pleasant calculation to do, you know, if you're using dx dy, right? Or dy dx, or either way. It's, yeah. But if you're using u and v, then this is either both vertically simple or horizontally simple. So whether you use dv du or du dv really doesn't matter. They're basically just equally as difficult. Just don't forget the 1/3, right? The determinant of the Jacobian, or the absolute value of it, I should say. So you'll need that when you do your double integral, right? So that's why you might want to convert from, say, x and y to u and v. Perhaps one reason is to make the double integral easier to calculate. When you transform it to an iterated integral using Fubini's theorem, right, the one on the right here, the rectangle, is going to be a bit easier than doing the one on the left here, which is neither vertically nor horizontally simple, and would have to be divided into three pieces, right, 3 regions. And so you're doing 3 separate iterated integrals. Whereas if you transform it, yes, it's a lot of trouble to do that, but once you do that transformation, right, I'll call it T for transformation. Once you do that transformation, you're down to a single integral, and probably a very easy one at that. You know, depending on what f is, depending on what the function you're integrating is, right? So I hope that helps, right? And for those of you who have had linear algebra, you recognize this as a linear transformation. You know, not to get too deep into this, but you can think of, you know, performing this transformation from x and y to u and v is just a matrix here, right? So the original matrix here, going from uv to x and y, is just 4/3. Oh, let's bring out the 1/3, right? 4, -1, 1, -1. And you multiply this matrix here by u and v, oops, u and then v, and you get your x and y, right? This becomes x and y. Sorry, no fraction. Right? And so by just taking the inverse of this matrix here, right, if this is t, then t inverse, well, we did this the hard way, right? We did it just by solving the equations here. But that would give you, in terms of u and v, the matrix 1, -1, 1, -4. And if you multiply that times x and y, no fraction, you get your u and v. Okay, so yeah, so in this case, this is just a linear transformation. You know, what's different here is that we're thinking about these as vectors, I suppose, as column vectors, instead of how we usually do it as, say, row vectors. But when you get to linear algebra, or if you've had linear algebra, you're certainly comfortable with vectors in columns instead of rows. So if you're going to take linear algebra, get used to that. That in this class we've been doing vectors this way, and in linear algebra it's usually easier to write them this way as a column instead of a row. And that's just so that you can do the matrix multiplication a little bit easier. I mean, you could do it with a row vector too, right? It's just the reverse. You have to put the x and y on the left, and then the matrix on the right, right? And then you get your u and v as a row vector here. Yeah, let's not get into that, right? So yeah, this is not a linear algebra course, but you can see the connection here. Thinking about these transformations as linear transformations. Now, of course, the first example we did where we had u times v was not a linear transformation, and so, right, so in some cases it's not going to be this simple because your matrix might depend on, say, u and v or x and y or something like that. But here they're just constants. Here they're just constants, right? 4/3, 1/3, -1/3 are just numbers. So. And that's really all there is to this section, right? I don't, you know, there's not a lot of homework in this section because I don't want you to really get involved in the details here of these transformations. Mostly, I just want you to understand when you need to use a Jacobian. You need to use a Jacobian anytime you're changing coordinates from your usual x, y, or x, y, and z to any other coordinate system, right? Not just polar coordinates or cylindrical or spherical, but any other generic coordinate system, say u and v, or, you know, when you get to 3 variables, not equals, but transforming them to u, v, and let's say w, right? So then your Jacobian will be a 3×3 matrix, like we did for the spherical coordinates. And then, of course, your regions aren't going to be solid regions, so it'll be like a solid parallelepiped or something, and then you can transform it into a rectangular solid. So, right, so that would be in 3 dimensions. And of course, if when you get to linear algebra, you can do this with not just a 2×2 matrix, but 3 rows and 3 columns, or 4 rows and 4 columns, or 100 rows and 100 columns. There's no limit to this, right? So yeah, you're going to run out of letters if you want to do 100, say, a vector with 100 components. But, when you do that, you don't use, x, y, and z anymore. You use x1, x2, x3, and so on, up to x100. Or as a column vector would be, x1, ... x100. But I think I'll leave it at that. We're not gonna have any reason in this class to use more than, well, let's say more than 4 variables here. Usually just 2 or 3, but occasionally we might see one with 4, just to keep it interesting. Okay, so I think that's all we need here. Is mostly just know the Jacobian and be able to calculate it. Again, it's on your formula sheet, although it's not one that I tend to put on tests very often, but you never know. So you should have the idea of calculating the Jacobian matrix and then the determinant, and then don't forget the absolute value, because yeah, if you do use the -1/3 here, you might it might not work out. You might get the negative of the answers, so just be aware of that. Okay, good enough.